We continue with talks about Gruenberg-Kegel graphs. And the next talk will be given by Kristina Ilenko, who is a PhD student of Institute of Mathematics and Mechanics from Ekaterinburg. Yes, Kristina, please.
Thank you for the introduction. Good afternoon, dear participants of the conference. I would like to tell you about the result of research which were received with my supervisor, Natalia Vladimirovna Maslova. The topic of my speech is the recent results of studying Gruenberg-Kegel graph coincidence of some non-isomorphic finite groups. So let's start. In our research, we used standard definitions and notation. So we use the term group while meaning finite group. We use the term graph while meaning a directed graph without loops and multiple edges. The subgroup of group G generated by all minimal non-trivial normal subgroups of G is called the circle of G and is denoted as you can see on the slide. A Frobenius group is a group G containing a proper non-trivial subgroup H, such that for all G in the difference of the set H from the set G, the following equality holds. Any Frobenius group is a semi-direct product of F and H, where F is a non-trivial normal subgroup in G. The subgroup F is called the Frobenius kernel of G, and H is called a Frobenius complement of G. A two-Frobenius group is a group G, which can be represented in the form ABC, where A and AB are normal subgroups of G. AB and BC are Frobenius group with Frobenius kernels AB and Frobenius complements B and C, respectively. Note that any two Frobenius group is solvable. Now I would like to give you an example of a Frobenius group. So let F is a finite field and order of multiplicative group is equal to Q minus 1. Let multiplicative groups act on an additive group by the rule on the slide. Now let's try to form a semi-direct product with respect to this action. After that, we can call G as a Frobenius group with the Frobenius kernel, which equals to an additive group, and a Frobenius complement, which equals to a multiplicative group. Now I would like to recall a few more definitions. Group G is called simple non-abelian if G has no proper non-trivial normal subgroups and no two elements in the group G commute. Group G is called almost simple if the following conclusion holds for some simple non-abelian group G0. Group G is called nilpotent if G has an upper central series that terminates with G. Let G be a finite group, so the spectrum omega G is the set of all element orders of G. The prime spectrum pi G is the set of all prime divisors of order of G. We use the term Gruenberg-Kegel graph or the prime graph of G while meaning the graph gamma G, whose vertex set is equal to the prime spectrum of G and two distinct vertices P and Q are adjacent if and only if in G we can find an element with order which is equal to a product between P and Q. Note that the research of properties of a finite group by properties of a Gruenberg-Kegel graph has been actively developing since the beginning of the 21st century. Namely, cases of coincidence of Gruenberg-Kegel graphs are actively studied. This research allows us to draw an analogy between the complex internal structure of groups and the less complex structure of its Gruenberg-Kegel graphs, which in the future may contribute to expanding the range of applicability of the finite group theory. Let's recall a Gruenberg-Kegel theorem. The Gruenberg-Kegel theorem describes all groups with a disconnected Gruenberg-Kegel graph, so it is a useful and interesting result. If G is a group with disconnected Gruenberg-Kegel graph, then one of the following statements, which you can see on the slide, holds. From the first, it follows that G is a Frobenius group. From the second, it follows that G is a two-Frobenius group. And from the last, it follows that G is an extension of an nilpotent group by a group A, where the following conclusion holds. And S is a simple non-abelian group with a disconnected Gruenberg-Kegel graph. We were interested in the problem of coincidence of Gruenberg-Kegel graphs of groups taken from the statements of the Gruenberg-Kegel theorem. In other words, let G be a finite, almost simple group, and H be a Frobenius group or a two-Frobenius group of the Gruenberg-Kegel theorem. And then the main problem of our research is a description cases of coincidence of graphs gamma G and gamma H. Now I would like to cite the results of previous researches on the Gruenberg-Kegel graphs. In 2012, Mariana Zinovьeva and Viktor Mazurov considered the cases of coincidence of graphs when G is a finite simple group and H is a Frobenius or a two-Frobenius group. In 2016, Mariana Zinovьeva and Anatoly Kondratyev determined the list of all finite almost simple groups such that all connected components of their Gruenberg-Kegel graphs are cliques. In 2018, Ilya Gashkov and Natalia Maslova showed conditions when Gruenberg-Kegel graphs of finite almost simple group and some finite solvable group are coincide. Thanks to results obtained in 2016 and 2018, we know all the cases of coincidence of gamma G and gamma H when G is a finite almost simple group and H is a solvable Frobenius group or a two-Frobenius group. And the case of coincidence of gamma G and gamma H when G is a finite almost simple group and H is a non-solvable Frobenius group is the last case, which earlier is not considered. And in our work, we explore this case. In other words, this work is relevant because it was necessary to complete the description of cases of coincidence of Gruenberg-Kegel graphs of finite almost simple groups and of Frobenius or two Frobenius groups. Let me remind an important case. In 2016, Halim Ahmudifar constructed a non-solvable Frobenius group whose Gruenberg-Kegel graph coincides with the Gruenberg-Kegel graph of PGL 249. That is a separately given almost simple group. His research confirms that the problem of coincidence is interesting. But we can understand when the non-solvable Frobenius group exists and when it does not for all groups with the so-called L2Q. So if G is a finite almost simple group and its so-called is equal to PSL2Q, and H is a non-solvable Frobenius group such that the Gruenberg-Kegel graphs are equal, then Q belongs to the set on the slide, and G is a group from the list on the slide. And for each group G, from the list there exists a non-solvable Frobenius group H, such that their Gruenberg-Kegel graphs are equal. On this slide, you can see the main result of our research. So let G be a finite, almost simple group. H is a non-solvable Frobenius group. Assume that gamma G and gamma H are equal. Then one of the following condition holds. From the first, it follows that so-called G is a sporadic group and G isomorphic to the automorphic group by M12 group. From the second, it follows that so-called G is an alternated group and G isomorphic to S7 group. And from the third, it follows that so-called G is an exceptional group of Lie type and G isomorphic to the automorphic group of T's group. For classical groups, we obtained that either G is isomorphic to the one of the groups listed in the items 1, 2, 3, and 4, or G is a small group with so-called PSL3Q or PSU3Q, for which the statements on the slide are true. And our research is still in progress. Let me now consider some tools which were useful in our work. In our research, it was important for us to understand what Gruenberg-Kegel graph of a non-solvable Frobenius group looks like. The first is a proposition which is obtained in a research by Mariana Zinovьeva and Viktor Mazurov. So let H be a non-solvable Frobenius group, then gamma H has two connected components. The first component contains 2, 3, and 5. Moreover, if P and Q belong to the first component of gamma H, then P and Q are non-adjacent in gamma H if and only if the set which consists of P and Q and the set which consists of 3 and 5 are equal. And the second component is a clique. For each labeled graph gamma with properties that indicated on the slide, there exists an unsolvable Frobenius group H such that gamma H and gamma are equal. And to solve our problem, we need a list of almost simple groups whose Gruenberg-Kegel graph has these properties. The next tool is the theorem, which is an important number theoretic tool when working with a Gruenberg-Kegel graphs. Let's start with the definition. So if R is an odd prime and Q is a natural number which is more than 1 and coprime to R, then there exists a number which is denoted as EQR and which is equal to minimum of all E such that Q to power E is equal to 1 modulo R and E is a natural number. So let Q be a natural number which is more than 1. Then for all natural M, there exists a prime R, which denoted as this, such that EQR and M are equal, except cases on the slide. And the prime R, which satisfies the condition on the slide, is called a primitive prime divisor of Q to power M minus 1. The next tool is the Gerana lemma. Let P and Q be primes and A and B be natural numbers such that the difference between P to power A and Q to power B is equal to 1. Then one of the statements from the slide holds. And the last tool is the lemma on the slide. Let Q is equal to P to power K, where P is more or equal to 7, and K is a positive natural number. Then, if the equality on the slide holds, then Q belongs to the set of 11, 19, and 49. That is all. Thank you for your attention.
Yeah. Thank you so much, Kristina, for the nice talk. Are there any questions or comments?
I have a question.
Yes, please.
Can you please move to the 12th slide? Yes, it is mentioned that the result is still in progress. What cases or some things that are left to prove, or is everything is proved? And
recently we considered the case when the case for PSL2 Q, we considered this more accurately. And now we work at the last case when circle G is equal to the this set. And so G is a PSL3Q or PSU3Q.
So there are left two infinite series for circles. Okay, thank you.
I make a comment.
Yes, sure.
Possible infinite series. I'm not sure that there will be infinitely many groups here. We need to consider two infinite series and possible exclude most groups from them. Really, in this problem, the most hard cases are when groups are small. For example, in PSL2Q, really there were some very interesting arithmetical equations like Pell equations, and we were forced to think more about numbers than about groups. However, group theory is rather non-trivial here too.
Yeah, thank you, Natasha. Are there any other questions or comments? And maybe a small question: did you use computer calculations towards the proof of the main result? Maybe
no, maybe only for check our results, but we try to use only mathematicians.
Because it
results.
seems that there are many different cases. So, but okay.
Yes, you are right, and really we used computer for conjectures and to check all the calculations we have made,
yeah,
but not directly to prove.
Yeah, I understand. Yeah. Are there any other questions or comments? If not, let us thank our speaker again, and